Hi ladies and gentlemen. In the last class and video I told you about random variables and their cumulative distribution function and probability density functions. So the probability density function is used to characterize the random variable. So based on this PDF, we can compute the averages or statistical averages of random variables. So the statistical averages can be used as a benchmark in decision making. So this presentation tells you about the computation of statistical averages, and let me start with that presentation. This speech is organized in your learning outcomes, the expression for statistical averages, and the decision making based on statistical expectations. Then I will show you a demo of a game that details that tells you about the Saint Petersburg paradox. It will demonstrate that decisions are not always based on statistical expectations. So statistical expectations are not the only benchmark for making decisions. Then the summary of understanding. So you will learn about statistical averages such as mean and variance. So mean is often the average value of a random signal if we talk about electrical signals, and variance is the power in a random signal. Then you will learn to use statistical averages in decision making. Then you will learn that high expectations alone cannot be used as a benchmark in decision making. It is one of the benchmark for decision making. See, suppose I have a random variable x with the PDF say fx alpha, then the nth order statistical average, that is the expectation of x raised to n, that is equal to minus infinity to infinity alpha raised to n fx alpha d alpha. So this E operator, that is called the expectation. What we do is, if you want to compute the expectation of x raised to n, then I have to multiply this dummy variable alpha raised to n. You take the nth power of alpha, you multiply by fx alpha and integrate from minus infinity to infinity. That gives you the nth order expectation. So with n equal to 1, it defaults to the mean. That is very important. That is the first moment or mean, mu, usually denoted by mu. That is expectation of x, it is minus infinity to infinity alpha fx alpha d alpha. Well, here I assume that x is a continuous random variable like a Gaussian type variable or a uniform type variable where this fx is a continuous function. There are some cases like the binomial distribution, etc., where these values are discrete. They are discrete probabilities instead of a continuous PDF. So there it will default to a summation. I will come to that. The nth order central moment is computed around the mean value. Often people are interested in the central moment, meaning that expectation is computed around the mean. Like the mean is subtracted off from the random variable, and the nth order expectation is computed. Expectation of x minus mu raised to n, this is equal to minus infinity to infinity alpha minus mu. So from every alpha, this mu value is subtracted off and raised to n fx alpha d alpha. So second central moment is of extreme importance, that is a variance. So variance of x is expectation of x minus mu whole square, here n becomes a 2, expectation of x minus mu whole square, that is equal to minus infinity to infinity alpha minus mu whole square fx alpha d alpha. So that is how I compute the variance, expectation of x minus mu whole square, that is the second central moment. The square root of variance is the standard deviation sigma. The square root of variance is the standard deviation. Well, if these random variables are discrete, like if it's a kind of a coin toss or something where a head has a probability of p and tail has a probability of 1 minus p, or if it is a summation of such a thing, like if it's a binomial distribution, they are all discrete kind random variable. So if it's a discrete type random variable, that integration becomes a summation. So mu is equal to expectation of x, that is I from minus infinity to infinity, alpha I pi. Okay, alpha I pi, and variance of x, that is I from minus infinity to overall possible I, alpha I minus mu whole square into pi. Okay, so here I have another result, expectation of x minus mu whole square, that is equal to expectation of x square minus 2 mu expectation of x. There is a small mistake here, I should close this here. Expectation of x square minus 2 mu expectation of x plus mu square, so it becomes expectation of x square minus 2 mu into expectation of x, that is mu, so 2 mu square plus mu square. Now you can see that expectation happens over the random variable alone and not over mu. So it is mu square expectation of 1, that is a 1, so it is mu square. So it becomes expectation of x square minus 2 mu square plus mu square, it is expectation of x square minus mu square. What is mu? That is expectation of x, so it is expectation of x square minus expectation of x whole square. Expectation of x is mu. Now what is this? This is my sigma square variance, so I can see that I can transpose this mu square to this side, so that it becomes expectation of x square equal to sigma square plus mu square. This is an interesting result. Now you can see that I make decisions based on, sometimes I make decisions based on statistical expectations. Suppose I am offered a lottery ticket by the vendor. Now, is it wise to take this lottery ticket? I can make a decision based on the statistical expectation. Suppose that the ticket price is 100 rupees and the prize money is 10 million. So it is ensured that in such case, it is ensured that the tickets are sold among 1 million people, say. Now, that being the scenario, is it profitable to buy a ticket? Now I have to compute the expected gain and loss. So the loss here is I lose 100 rupees when I pay for the ticket. In the real chance of winning this, I get 10 million. This is my gain and this is my loss. Now this loss and gain, they do not matter much. You have to compute the expected value of the loss and expected value of the gain and then compare. That only makes sense. So for computing the expected gain or loss, I have to multiply them by the probability of win and loss. Okay. So if 1 million people take this lottery, what is the probability of a win? That is 1 by 1 million, that is 10 raised to minus 6. And the expected value of the prize money or expected gain, if you win the lottery, in the rare case of winning the lottery, what is the expected gain in that? That's the probability of win into the prize money. So it is 10 raised to minus 6 into 10 raised to 7. That is 10 rupees. Okay. So the expected gain in the event of winning, that is 10 rupees. Now, what is the probability of a loss? That is 1 minus P win, that is 1 minus 10 raised to minus 6, approximately 1. Okay, so what is the expected loss? So 1 minus P win, this is the probability of loss, into ticket price, this is my actual loss. So 1 minus 10 raised to minus 6 into 100, this is 100 rupees. Now the expected loss is 100 rupees and the expected gain is 10 rupees. So it is wise not to take this lottery ticket. It is foolish to take this lottery ticket because the expected loss is 10 rupees and expected gain is 10 rupees. I am sorry, and the expected loss is 100 rupees. Likewise, if you see in the supermarket, if you go to the supermarket and if you take things like packed sugar or packed flour like Ashirwad Atta or something, they come in packs of say a kilogram. If you take a kilogram pack of Ashirwad Atta or something, and if you weigh it precisely, you can see that the pack contains more than 1000 grams. You expect 1000 grams and exactly 1000 grams in that, but you may get more than that, like 1004 grams or 1005 grams, slightly more than 1000 grams. Why this is? Because actually they incur a loss when they give some 4 or 5 grams more to you they incur a loss in that. But why do they do is there is a reason based on statistical expectations. Why this happens is probably a day they pack 1 million packs of 1 kilogram of flour. So these are done by automated machines, and an opened cover comes before a dispenser that dispenses flour into that. Then it is automatically sealed. So this may be happening on a very large number of packs. So if the dispenser is set at say exactly 1,000 grams, sometimes there may be an error in it. Sometimes some cows may be getting some packs may be getting say 998 grams only or 995 grams only. Okay, so that error will have a Gaussian distribution. If the number of samples is very large, then that error will have a Gaussian distribution. So what they do is, instead of setting at 1,000 grams, they may set this dispenser at say 1,004 grams or 1,005 grams, so that even if there is some error in it, every packet will have slightly more than 1,000 grams, none with a weight below 1,000 grams. Why? Because if some of these have smaller than 1,000 grams, smaller weight than 1,000 grams, then the government official, the Weights and Measures Department, they can fine the company. So that fine will be much more. The expected value of that fine will be much more than the loss incur when they give some 4 or 5 grams more in each packet. So likewise, there are many scenarios in which this expected gain and loss play an important role in your life. So if you go to the local apple vendor, and if you ask for this is very interesting, if you go to the local apple vendor and ask for a kilogram of apple, you can see that sometimes he put a few apples in that. Then he looks at the weight; it is slightly more than 1,000. Okay, then he replaces one apple by a smaller apple, ensures that you get around 1,000, slightly more than 1,000 grams. Okay, but not 1,000, not exactly 1,000, or slightly less than 1,000. Slightly less you don't accept. Even 1,000 he does not give. Instead, he may be giving some slightly more than 1,013 grams or 1,015 grams, slightly more than 1,000 grams. So it is all due to the principle of statistical expectations. Now, one care should be taken here, that is, a high expectation alone is not the decision-making factor. For example, let us look at this game. Let us look at this paradox called St. Petersburg paradox. It's a betting game in which a player enters by paying a fee. Of course, for every betting game you have to pay a fees first, and then you play it. Then he tosses a fair coin repeatedly. So he is paid 1 rupee for the first head, 2 rupees for the second head, 4 rupees for the third head, 8 rupees for the fourth head, etc. But if a tail comes, then the game stops. Okay. So if you compute you may think that the statistical the gain will be you will get significant gain in playing this game, but it is not the case. But if you compute the statistical expectation of this payoff, you can see that the expected value, say suppose he starts playing and he gets a first head, the probability then he gets 1 rupee. So the expected gain is 1 into 1 by 2, because probability of getting a head is 1 by 2. So that into the payoff, that is 1 rupee, that becomes a half. Then if he gets a head again, he gets 2 rupees, double of that. So that 2 into what is the probability of getting 2 heads in succession, that is 1 by 2 into 1 by 2, which is 1 by 4. So this expected gain will be 2 into 1 by 4. Then if he gets 3 heads in succession, he gets 4 rupees. Okay, so what is the probability of getting that is 1 by 2 into 1 by 2 into 1 by 2, that is 1 by 8. So 4 into 1 by 8 plus 8 into 1 by 16 plus etc. So it is 1 by 2 plus 1 by 2 plus 1 by 2 plus etc. up to infinity. These are all 1 by 2. So it is an infinite sum of 1 by 2, which is infinity. You can see that the expected value of this random variable, this payoff, is infinity. So you think it is profitable to play this game, but I I will show you a demo of this game, and you will very quickly understand that it is not wise to play this game. Even though the expectation is very big. So this demonstration is to let you understand that a high positive expectation alone is not a decision making factor. So I will show you a demo of this. Here I have the code for this. Here what I do is I import two scientific modules. The first one is a SciPy, it's a scientific computing Python module. I import everything from SciPy, or you can have some selected thing. For the sake of simplicity, I imported everything. And this PyLab also I imported. I don't know whether I will be using that, but anyway I imported that. So here I put a price array, a blank array. This will hold my price, like if I get a first head, I will get 1 rupee. If I get 2 heads in succession, the 2 will be added to that. If I get 4 will be added to that way. Okay. So if I sum up this price array, that will be my total price amount. Okay. Then I enter the maximum number of trials. So it may be allowed to play for a finite number of trials. So that I can enter, that I convert to an integer. Then for I in range 0, n, I toss a coin. This is a fair coin, sign rand minus 0.5. This 0.5, this threshold makes sure of 0.5, this ensures that it's a fair coin, this thing. So x will be a value either a 0 or a 1. Then you print the outcome, whatever. Then if x equal to 1, you append 2 raised to I to this price array. Okay. If I equal to 0, it is 2 raised to 0, that is 1. This 2 star is a power, 2 raised to I. 2 raised to 0 is a 1. If it is 0, first I get a head, I add 1 to this. If I get I equal to 2, I equal to 1, it will be a 2. Then I equal to 2, it will be a 4, that way. But if this x is a 0, that means a tail has come, then the game is entered and the total payoff will be displayed, and the program will be exited. Okay. Now let us run this code here. I run Peter. Peter is the name of that. Okay, now enter the maximum number of trials. I put as 12. So you can see that the first one is the first outcome was 0. That was a 0. So the game ended. Okay, you didn't get anything. Total the payoff is 0. Again I play this. Again I got a tail in the beginning. My game ended there. So here again I give again you get 0. You can see that you don't get any money. I play this again. This time first a head has happened. So what happened is I got 1 rupee. Okay. So again something. Now I got 2 heads in succession. So I got 3 rupees. 1 rupee plus 2 rupees. That is 3 rupees. Now you can say that again I got nothing. I am trying for all this I have to pay the money. So you can see that I am getting very small amounts. Here I got 1, 2, 3 in succession. I got only 7 rupees. Okay. You don't get anything here. You can see that your payoff does not increase much. Okay. Your actual payoff is very small. You compute the statistical expectation to be very high, but you can see that your payoff is very, very limited. So this is a demonstration of St. Petersburg paradox. Now the summary of understanding. You learn the statistical averages such as mean and variance. Then you learn to use statistical averages in decision making. Then you understood that the high expectations alone cannot be used as a benchmark in decision making. There are many other parameters also. Then you observe the demo of St. Petersburg paradox, and that is the end of this presentation. I thank you all.